How much math do you want? As deep as the ocean? Brilliant. I was trying to decide how much math to actually include in this series, but it seems you guys just want all of the math, so welcome to this episode of my ray tracing series, where we're going to do some mathematics. In all seriousness though, ray tracing of course does involve a lot of math, lots of rendering and graphics programming does in general. So over the course of this series, I am going to try and include like as much math as possible. I'm not going to go down into the extreme depths of the ocean, even though that poll really wants me to, both because I am not like a professional mathematician, and also because I feel like I will lose a lot of people in this series if I just talk about math all day. Remember, at the end of the day, this series is still meant to be practical. However, if you actually understand the math that goes into what we're doing in this series, not only is it really helpful for the future, it's also just really interesting. So yeah, buckle in. So first of all, if you haven't seen the first episode of the series, then I'll have it linked over there. Highly recommend you check it out because it explains what this series is, what we're doing, all that stuff, so that I don't have to waste time here explaining everything. So our first goal along this epic journey is going to be to render a sphere, like this. What you're seeing on the screen right here is going to be our step 1. I want to be able to specify a camera somewhere in 3D space, a sphere somewhere in 3D space, and then generate an image which describes this scene, which shows this scene. Now this is in fact a sphere. It looks kind of like a circle because it's completely flat shaded. We can't actually tell that it's a sphere because it's just a constant color. But if we add a little directional light over there somewhere and do some very basic lighting calculations, then you can see that we can now see the form of the sphere a little better. It is in fact a sphere. I told you so. So why a sphere anyway? Why not like a cube or some kind of other shape? The reason why we love spheres so much is because they're extremely simple to define mathematically. All spheres are just like a 3D coordinate which defines its origin, where is it in the world, and then just a radius which defines how big the sphere is. That's all you need, just a three-dimensional point and a radius. So where do we begin if we want to draw this sphere? Well, in today's episode, what we're going to do is deep dive into the math that we'll actually need to use in order to draw this sphere. That is to send rays out from the camera and see if they actually intersect the sphere. And we'll also talk about what a ray actually is, like mathematically, and what a sphere is mathematically. And the best part is we're going to do all of this math by hand, like on paper. That's right. Ray tracing on paper. However, we are going to make a small compromise. Instead of doing all the math that we need to do in 3D, we're actually going to take it down a notch and do all this math here today in 2D. However, there's really not as much difference as there might seem between 2D and 3D in this case. Really, the only difference is that a sphere will have a Z component. It will have as like a Z dimension, whereas a circle, which is what we're going to be talking about here today, does not. It's just got X and Y. The result is just a little less math that we need to do, but the math extends into a third dimension really easily, and we'll talk about that here today as well. Since obviously when it comes time to writing our actual ray tracing code, we will need to be dealing with 3 dimensions. Now the math that you'll already need to know in order to follow along with this video is fairly simple. It's just like high school level math really. However, if you want to revise your math, or if you find that you're not getting certain parts of this video, then I highly recommend you take a look at Brilliant, the sponsors of today's video, because Brilliant is my first choice for math courses. If you don't know what Brilliant is an amazing website filled with courses on various STEM topics, and I particularly love their math courses. Unlike other course websites, Brilliant's courses are extremely engaging and interactive. They show everything visually, they quiz you on the content that they teach you, and they also give you like these amazing interactive elements to play with that just helps you learn. This kind of visual and practical learning is, I think, by far the best way to learn this kind of stuff. Because if you're actually seeing it and then putting it into practice, like we will be doing in this series as well, you'll just retain the information and learn it much faster, and it'll be way more effective. Brilliant's math courses cover a huge range of topics, including plenty that will be very, very useful for this series. In fact, I actually used Brilliant myself to revise some of the math that I would need for this series. Not a joke, I'm being 100% honest. They've also got a bunch of other courses on like computer science topics, data structures, neural networks, that kind of stuff, if you're interested in stuff other than math. The best thing about Brilliant is that you can get started for free. Just go to my link in the description below, brilliant.org/thecherno. And Brilliant have been nice enough to offer the first 200 of my subscribers who go to that link in the description below 20% off an annual membership. So yeah, definitely go check out Brilliant. It's honestly just a really good way to go over some math that you'll need for this series and for programming and for life. Huge thank you to Brilliant for sponsoring this video. All right, nothing else really for me to say here. Let's begin the math. So first and foremost, we have to understand what a line is. A line and a ray are kind of similar, but they can be interpreted differently depending on how you look at it. If we draw a basic Cartesian plane here, where we have a y-axis and an x-axis, one of the simplest equations we can possibly draw is a line like this, which has the equation y equals x. What this means is that for any given x value, so let's just say x is 2 over here, y is equal to x. So y will also be 2, and we know that for any point along this line, the x and the y values will be identical. This thing over here is your basic line equation. Now you can expand this a little bit. Y equals mx plus c probably rings a bell. That simply adds a slope to the line so that you can have a line that has a different angle or even goes down like this if it's negative. And then c is simply translating the line along that y-axis, because if x is 0 and this cancels out entirely, then we're left with y equals c, which means that for x equals 0, c determines where our point will be if x is 0 over here, what the y value will be. Now, if we go over here to Desmos.com, which is a fantastic online graphing calculator, I can just type in y equals x, and you can see we have our line over here. A straight line running through the origin where for any x value, the y value will also be the same. Now that's fantastic, but does it really help us with ray tracing? And is this a good equation to use? The answer is, well, not really, because this is an extremely simple equation that we can use for graphing. However, in the real world, we want to use vectors. And in fact, we want to use vectors that have an arbitrary amount of components, usually 2 or 3. What this means is that rather than expressing our equation like this, we want to be able to specify just a point somewhere in 2D or 3D space that is the origin of our line. So where does our line actually begin? And then we want to be able to specify a direction for that line to go in. And this kind of setup here is what you would call a ray. And that's how a ray differs from a line. Now, to be honest, I don't feel 100% comfortable saying that because everyone's definition of all of these terms might actually be different. But traditionally, a ray is something that contains an origin and a direction, usually expressed in terms of vectors. Now, as I mentioned in the first part of this video, we are going to be thinking of everything in 2D today. However, just because we are going to be talking about this stuff in 2D, meaning we'll have x and y components and no z component, you just add a z component and it becomes 3D, right? I want to make that clear, that all of this stuff translates extremely easily into 3D. It's just that it's much simpler to kind of draw and show this stuff and do the actual manual working out if we have one less component, one less dimension. So since we are in 2D, origin will have an x and a y component, and direction will also have an x and a y component. So these are just like vectors, basically. We have 2 component vectors here, where one of them is a point in 2D space, so a point somewhere in our world, which is the origin. And then we have a direction, which is where this actually points. Now, in order to actually define this line though, we need to be able to sample a point along the line somewhere. And this is where our magical t parameter comes in, which is really the distance of the point along the line. It's sometimes also called a scalar because it will scale the origin along the directional vector. However, if you're new, a good way to think of it is just the distance. So what that means now is that we have an origin. Now I'm going to give these slightly different names. I'm just going to call the origin A and the direction B. Why? Well, mostly because the origin looks like a 0 and it can get confusing, but also because A and B are really simple variables to think of. So if we have our origin over here, we can express this ray equation as A plus B and then that scalar value t. Now these two, of course, are being multiplied together. And since these are vectors in 2-dimensional space, A has an x and a y component, and B has an x and a y component. And to finish off this equation, we could say that a point along this line is equal to the origin plus the direction along with the distance along that line. And just to kind of test this out and show you what I'm talking about, if the origin xy was like somewhere here maybe, let's just say it's at 2, 2, and we had a direction for the line which was in the direction of 1, 1, so it's kind of going in the positive axes, both x and y, then if we wanted to find a point that was like, well, I don't know, 2 meters or 2 units down that line, we would simply set t equal to 2. And so if we plug it in with the rest of this equation, we know that that point, xy, will be equal to the origin, which is 2, 2, plus the direction, which is 1, 1, times t, which is 2. Now, I know that these are in vector form, which might make it look like it's a bit trickier to solve. However, we can actually separate these by axis. Does not matter here at all, since x and y are actually identical. They're both 2, and they're both 1 here, so we can just kind of ignore one of them. However, basically, if we just do this math, we have 2 plus 1 times 2, which is just 2 plus 2, which is 4. And so we know that the result here is 4, 4, which means that if you move along this line by 2 units, you will end up at 4, 4, which as you expect is the correct answer. So that's how we can kind of use this equation. Now, if you're paying close attention, you probably noticed that we moved more than 2 units along that line. We actually moved around 2.8 because we moved 2 units in the x and 2 units in the y to get 4, 4. The reason this happened is because our directional vector for our ray, b, is not a unit vector. You can see it's 1, 1. We would have to normalize that and bring it down to like 0.7x and 0.7y roughly. Then it would be a unit vector, and then we would in fact have moved 2 units along that line if we pass in 2 for t. However, it doesn't really matter for this example or for the rest of this video, so we'll just ignore that. 1, 1 is just a lot easier to deal with. Now, if t is negative, then we will go backwards from the origin, and that's totally valid as well. So because this line equation in vector form can be a little bit awkward to solve if the values aren't identical in x and y, we can actually split this up by dimension or by component. So in other words, px will actually be ax plus bxt, and then py, so the y coordinate, will be ay plus byt, right? So it's totally okay to just kind of split these two up, and these are often called the parametric equations. And of course, as you can imagine, if we did have another axis like z, we would simply have another one of these where we would have the origin z component and the direction z component here as well. Now, the reason these are called parametric equations is because we have a parameter in the line, which is actually t, the distance along the line. That should be fairly familiar to you if you're a programmer, which I assume most of you watching this series probably are. Parameter, variable, same kind of thing. Okay, so these two equations here are going to be quite important, so we're going to just remember them. Now, since we are in 2D, we're going to be focusing on circles and not spheres. Now, spheres and circles are remarkably similar. The only difference is that spheres, of course, have a z-axis, a z-dimension, and circles do not. So we've talked about the equation of a line and all of the various different forms that we might need to know. So let's talk about what it takes to actually draw a circle. Well, the equation of a circle is x minus a squared plus y minus b squared equals r squared. So what on earth does this mean? Well, x and y are basically just our coordinates along this plane somewhere. So you can kind of ignore those the same way that we would ignore y and x over here, since that's what we're actually showing. A and b, however, are basically the coordinates of the circle's origin, and r is the radius. So if we look at a circle like this one here, we can see that the origin is 0, 0 over here because it's centered at the origin. And then we have some kind of radius that defines a circle. So it could be something like 1 or 2. And of course, if it is 2, then we would have a point over here, which is 0, 2, and a point here, which is 2, 0, because we know that the radius is going to be 2 units. Now, if we are going to be dealing with a circle that is in fact centered at the origin over here, that means that A and B are just 0, 0, which means that if we plug in 0 into A and B over here, you'll see that we of course get x minus 0, y minus 0, which is just the same as x squared plus y squared equals radius squared. So this will just simplify the equation here. Now let's give our circle a radius. So sure, let's go with 2. So what that means is that our equation now looks like x squared plus y squared equals 2 squared, which is 4. Now the next step is going to be to take this and graph it. To make it a little bit easier for ourselves though, let's rearrange this so that it actually looks like it's in the same form as this equation over here. So I want it to be y equals something. So to do that, let's go ahead and move x squared to the other side of the equation. So we'll have y squared equals 4 minus x squared. And then to get just y, we'll have to square root both sides. So we'll have y equals the square root of 4 minus x squared. Pretty simple, pretty basic algebra. So now that we have the equation in this form, let's go ahead and go to our graphing calculator and we'll type that in. Y equals square root 4 minus x squared. All right, check this out. We get something. However, it looks like we've just got half a circle, a semicircle, in the positive y axis. Why is that? Now, I'm not going to get too deep into this, but what I will say is that the problem with square roots, as you may already know, is that there are essentially multiple solutions, 2 solutions commonly to a square root. Why? Well, the square root of 4 is 2, because 2 squared is 4. However, minus 2 squared is also 4, because minus 2 times minus 2 is a positive value, 4. So therefore, how do we know if the square root of 4 is positive 2 or negative 2? And the answer is, we do not know. It could be either one. there are literally multiple solutions, two solutions to this problem over here. And so because there are multiple solutions to this, if we want to actually see our entire circle on the graph, we need to basically have a plus and a minus on the result of the square root, because we know that if we have a real value there, meaning a value inside the square root that actually amounts to being above 0, because we can't have the square root of a negative number, that's an imaginary number, and we're only sticking to real numbers here today, we can just show the positive and the negative solution. So if we copy our equation here and basically paste it into here, but flip this to be a negative, then you can now see that we have our complete circle because we're taking into account both of these solutions. Okay, wonderful. So we've basically graphed this problem here that we're going to be spending the rest of today solving. And that is, if I do in fact have a ray that originates, well, let's just say at like -3 over here, and if that ray goes in this kind of direction of positive 1x and positive 1y, how do I know if it actually collides with this circle and where it collides along this circle? So we can actually see visually what the solutions are. They're around -1.41, which is just the square root of 2, and positive 1.41. However, seeing it visually like this is all great, but if we're going to be writing a computer program to do this for us, then we're going to have to set this up in terms of equations, not just visually kind of winging it. Even though, yes, in mathematics, of course, this is a valid way to solve equations. But the cool thing about seeing it visually like this is we know we have a way to basically double check our working out and make sure our solution is correct because we can visually see these 2 points of intersection here. So going back to here, how can we actually solve this equation? And in fact, in case we're getting a little bit lost, let's talk about how this relates back to ray tracing. So first of all, we discussed what the equation of a circle is. It's basically this thing here, right? Now, can you guess what the equation of a sphere is? Well, you'd be very correct if you guessed that it's exactly the same thing, however, with that z component. So we basically also have a z minus c, which is that third component of the sphere's origin. And then if we wanted to move this radius onto this side, we could just do that and then have it equal 0 like that. So this is the equation of a sphere. Extremely similar to the equation of a circle. The only difference is, of course, we just don't have this area over here if we are dealing with a circle. And so we end up with just this. And that is our circle. So when we're actually trying to render a sphere in our ray tracer, the math that we're actually doing is very similar to what I've shown you here in 2D. We basically have this image of a sphere, which I showed in the beginning of the video. That's kind of what we're aiming to achieve. And we can see, if we play around with some lighting, that it is in fact a 3D sphere, even though if it's flatly lit, it kind of looks like a circle. But no, it does in fact have volume, because the math that we're doing for it is 3-dimensional. And so if we look at how we synthesize this image from the side, right, what we're kind of doing is we're shooting out all these different rays, which accounts 1 per pixel. And so over here in our side view, if we have our camera, we have our sphere over here, this thing here is our camera, then what we're actually doing is shooting out all these different lines here and then seeing where they intersect the sphere. And wherever they actually do intersect the sphere, we're setting that pixel, whatever coordinate that pixel lies at, we're setting that pixel's color to be a particular value. Now this could be calculated if we're doing lighting, it could be a flat color if we're just doing a flat color. But the point is, we're able to know that the line here actually hits this sphere, and then we can do something with that result. Either figure out where it hit the sphere and then do some extra calculations, such as figuring out what the normal is of that particular point in 3D space, or even just a simple binary yes, no, did we hit it is enough to just shade it a flat color. If, however, our ray misses the sphere and there is no collision, then we can just return whatever the background color is, basically. Or in a more complex scene, maybe we have other objects to test for, but for now we just have a single sphere. So if we forget about the third dimension here, and we go back to what this looks like, you can imagine that our camera might be somewhere at -3, and then this ray, this line here that represents a ray, that is just one of the rays that we're sending out for one of the pixels that we're trying to determine the color of, that's going to be rendered in our viewport. And this circle, of course, is that sphere, but in 2D space. So our job at the moment is having the equation of this circle well defined, and having the equation of the line, the ray, well defined. I want to work out, using the power of math, if this ray intersects this circle and where exactly it intersects the circle. And again, the beauty of this is that if I can do it like this in 2 dimensions, then I can easily do it in 3 dimensions. The only difference is going to be that extra z-axis, and that is it. So let's go ahead and solve it. So the first thing that I actually want to do is kind of just define what our actual line and circle look like. So we know that the line, if our equation here for that is going to be a plus bt, we know that a is going to be minus 3, because that's where we've decided that line is starting. Minus 3, this point over here. And then it's heading in a direction of 1, 1, which is just going to basically have it go 1 unit positive x-axis for every 1 unit that it climbs up in the positive y-axis as well. We don't really have to worry too much about this being a unit vector, by the way. So this is our kind of complete line. Now for our circle equation, which we know is x squared plus y squared minus r squared equals 0, if it is centered on the origin, there is no a and b component, which in fact the circle's origin is 0, 0, so there is no a and b component. And the radius squared we've decided is 2. So this circle over here has a radius of 2, as we can see. So that means that really r is just equal to 2, which squared is 4, but we'll just write it as 2 like this. So this is actually enough information to work out where the hit takes place. So how do we actually do this? Well, we're simply going to just solve this equation, and we're going to do so by using the powers of substitution to begin with. So the first thing we're going to do is a, of course, has 2 components, x and y. B also has 2 components, x and y. So what we're actually going to do is write this per axis, per dimension. So in other words, this equation kind of splits up into 2, where we have ax plus bxt, and then also ay plus byt, right? These are kind of our 2 equations. What we're going to do is we're going to plug this one into the x and this one into the y of this equation here. So what that means is that this equation becomes ax plus bxt squared plus ay plus byt squared minus r squared, which is just 2 squared, which is 4. So I'll just write minus 4 equals 0. Now at first glance, this might look completely useless, but let's just continue simplifying this. We're actually going to expand these brackets and see what we can come up with. So if you remember how to expand brackets, it's a bit of a pain, and also this is one of the reasons why I decided to go with circles, not spheres, so we'd have less brackets to expand. But basically, ax plus bxt squared, right, is the same thing as just this. So we have 2 copies of this, and to expand these brackets, remember, you have to basically multiply each component here with each component here until you've gone through like all of the combinations. Now the beauty of this though is that if we expand this one bracket here, we know that it's going to be the same for this second bracket here, except instead of x we're going to have y. So we only really need to do this once, which is a good thing. So ax times ax gives us ax squared. Man, I feel like a high school math teacher at this point. Then the next one over here is going to be ax times bxt, which is going to give us ax bxt. Then we have bxt times ax, which is actually the same thing. So I'm just going to sneak a 2 in here because we have 2 of these. And then we have bxt times bxt, which gives us bxt squared. Now this whole thing is actually squared because we have the multiplication of 2 components here. And actually, since we were all about simplifying this by removing the brackets, we might as well write this as bx squared t squared. So that is that bracket expanded. So if I also do the same thing here, and I just copy this but replace the x's with the y's, because we know it'll be the same, we have ay squared plus 2ay byt plus by squared t squared. That's all of it. And then minus 4 equals 0. Now that is a monster of an equation here. However, we notice a trend here. Now remember, what we're actually trying to solve, we have the equation of the line, we have the equation of a circle. That's all well defined. What we're actually trying to solve for here is t, right? Because we want to know if there is a hit along that ray, if there's a collision along that line, and where that collision is. So the cool thing about this is that we notice that this actually can be rearranged to be a quadratic equation. Now, a quadratic equation, if you remember, is like ax squared plus bx plus c equals 0. So the point here is that we have an x squared, we have an x that is not squared, and we can optionally have like some kind of constant value here. And that is exactly what we're seeing over here, but with t, right? We have t squared in 2 places. We have t by itself in 2 places, right? And then we have just some other terms like ax squared and minus 4 that is just like our constant term. So let's go ahead and kind of rearrange this so that we express it in terms of t. So what that means is that we're going to group all the terms that are t squared, which is just this one here and then this one here. So this is simply going to be bx squared plus by squared, and then all of that's going to be multiplied by t squared. So there's our t squared component. Then we're going to add in just the t terms. So this one over here and this one over here are our two t terms. So 2ax bx plus 2ay by t, and then plus our constant terms, which I'm going to put in brackets here. So ax squared, ay squared, and so this one here, this one here, and this one here. I'm just double checking that I've got everything, and it looks like I do. So ax squared plus ay squared, and then the minus 4, which I'll also put over here, equals 0. Okay, so now you can see quite clearly, hopefully, that we have a quadratic equation. Now, I've deliberately put it into this first before subbing in the actual values, because remember, we know these values. The only value we don't know is t. Bx and by are just the directional values, the directional vector of our actual ray. Ax and ay are just the origin of the ray. So we actually know everything except for t. But having the equation written out like this as a quadratic equation is great, because now we can just move the line around if we want to, and we've already got it in the right form, so really all we need to do is just plug in different values. And in fact, minus 4 dictates the radius of the circle. So if we want to make the circle smaller or larger, we can actually do that. The only thing we can't really do is move it away from the origin without kind of redoing this thing, but using the non-simplified equation, right? So I simplified it so that it was just, not x minus a and y minus b, but just x squared plus y squared. We'd have to sub in like this actual thing so that we have a and b for our circle, and then we could move it around if we wanted to. But I've just simplified this because, as you can see, the manual working out can be a little bit tedious. Anyway, so next step then is going to be to sub all of this stuff in. So again, a and b are the two things we need to sub in, or ax and bx, right? Which we know, if we go back to here, that ax is minus 3, ay is minus 3, bx is 1, and by is 1. So let's go ahead and sub all of that stuff in. So remember, a is minus 3, and b is 1, 1. So let's begin. So bx squared, so that's going to be 1 squared plus 1 squared for y, t squared, plus 2 times ax, which is minus 3, bx, which is 1, plus 2ay, which is minus 3, by, which is 1, all of that multiplied with t, plus ax squared, which is minus 3 squared, plus ay, which is minus 3 squared, minus 4 equals 0. Okay, now we simplify. So 1 squared is just 1, 1 plus 1 is 2. So this becomes 2t squared plus all of this stuff. So 2 times minus 3 is minus 6 times 1 is just minus 6, plus the same thing. So minus 6, which is minus 12. So let's just simplify that right now. We might as well. Minus 12t plus whatever this is. So minus 3 squared is 9 plus 9 again, minus 4. So 18 minus 4, which is 14, positive 14. Equals 0. Look at that baby. Much smaller and just a normal quadratic equation. So what do we do from here? Well, we just need to solve this quadratic equation. Now, programmatically, the easiest way to do this is probably to use the quadratic formula. The quadratic formula is a formula that we can derive by completing the square, which is another way to solve quadratic equations. That just gives us a really great kind of easy equation that we can just sub in all of our different coefficients here and see, first of all, are there any solutions and what they actually are, if there are solutions. So the quadratic formula is minus b plus minus the square root of b squared minus 4ac divided by 2a. That is something called the quadratic formula. And we're about to use this. So what is b, what is a, and what is c? Well, they are the coefficients to our quadratic equation here. Just going to move this over here. So a is going to be 2, b is going to be minus 12, and c is going to be 14. And so now you can see we can just plug in these values. Before we do that though, I want to focus on one specific part of the quadratic formula, which is this part inside the square root. This is called the discriminant. Now the cool thing about the discriminant is that if we plug in the values here, right? So A, B, and C, if we plug them into this part over here, the value that we get when we solve that particular part of the equation will actually tell us if there are any solutions and how many there are. So let's go ahead and do that first. So B squared is going to be minus 12 squared minus 4AC. So 4 times A, which is 2, times C, which is 14. So that's our kind of discriminant part. So let's go ahead and simplify that. So minus 12 squared is 144, minus 2 times 14, which is 28, times 4, which I think is 112. Let me just double check that. Yep, 112. Okay, so 144 minus 112 is 32. So 32 is the result of this kind of discriminant equation. What does it mean? Well, if we get a value that is greater than 0, that means that we have 2 solutions. If we get a value that is equal to 0, we have 1 solution. And if we get a value that is less than 0, so it's negative, we have 0 solutions. That's how this discriminant works. And remember, the reason that it works that way is because if we have a positive value inside the square root, then we know that it will be plus minus because there are 2 solutions to that square root, as we talked about earlier. If we have the square root of 0, however, then the square root of 0 is just 0. That's 1 solution. Plus minus 0, it's just 0. And finally, if we have a negative value inside the square root, like the square root of negative 1, then there are no real solutions to that. And that's why we don't have any solutions for that case. So it all comes down to the magic of the square root. So we can actually do just this very simple equation without having to do the square root or anything else to work out, do we have any solutions? Now, what on earth are solutions? What does that mean? And why do we care? Well, solutions are intersections. So you can see clearly that we should expect to get 2 solutions here because there are 2 intersections. We have this kind of entry wound and exit wound over here as our line pierces our circle. Now, if the line was somewhere else, so if, for example, we, I don't know, had it like plus 4 or something, we would expect that there would be no solutions because it doesn't hit at all. And if it was like extremely close and grazing it like that or something, but even closer, we'd have 1 solution because it would be like a tangent to that circle. So that's pretty cool because now you can see we can actually see whether or not our ray hits our sphere or our circle. Now, the cool thing is this is actually enough to just simply draw a circle, right? Because if we have more than 0 solutions, then we know that the ray has hit the circle and we can just return a color, whatever color we want our circle to be. And that is the color that we should shade that particular pixel that we've cast out that ray to. That's all we have to do. And if we get 0 solutions, well, maybe the ray is somewhere here and we're not part of the circle at all. So in other words, we don't even have to keep doing the quadratic formula, keep solving the quadratic formula here to work out the actual solutions to this equation. We just need to know, are there solutions? And if there are solutions, that's enough to draw a circle, or I should say a sphere in our 3D ray tracing case. However, for more detailed scenarios, we do actually want to know where we hit this circle or sphere. So for that, we're actually going to have to keep going with this quadratic formula. So we've worked out this discriminant part. We know that it's 32. So let's go ahead and sub that in. So we have minus b plus minus square root of 32 divided by 2a. So let's sub in a and b over here. And so we'll get minus 12 plus minus square root of 32 divided by 2 times 2. Right, which is, of course, just 12 plus minus square root of 32 divided by 4. Now, the square root of 32 is roughly equal to 5.66. So that's the value we'll kind of use here. So this will be 12 plus minus 5.66 divided by 4. Now again, we have this plus minus here because we know there are in fact going to be 2 solutions. And so if we work out both the solutions, 12 plus 5.66, 17.66 divided by 4 is going to give us 4.415. And then the minus solution is going to give us 1.585. So these are our 2 solutions. Now you might be wondering, like, well, okay, there are 2 solutions. We know there are 2 intersections, but that doesn't seem right. And like, what do I do with this information? Like, because these coordinates clearly are very different. Like, what's going on? Well, remember what we were solving for. We were solving for t. So this is the value of t, which is that scalar, that distance along that ray. Right? So what this actually tells us is how far along the ray the intersections took place. So we know that we have one about 1.5 into the ray, and we have one at 4.4 into the ray, right? So these are going to be our 2 intersection points. Now, since we obviously have a well-defined line equation, we can just simply plug in these values of t, especially because it's a parametric equation in terms of that t parameter. We can just plug in these values here and we will get actual two-dimensional points. Why two-dimensional points? Because we have two equations here, one for x and one for y. So what are the equations? Well, first of all, let's go ahead and copy this, and we will plop it right over here. So ax we know is minus 3. Well, actually, they're going to be the same, right? So ax and ay are the same, so we can just really do this once in this case. But minus 3 plus 1 times t, which is going to be either 1.585 for one of the intersection points, and this is going to be the same for both x and y since they are identical. And then minus 3 plus 1 times 4.415 for that other point. So really it's just going to be minus 3 plus 1.585 and minus 3 plus 4.415. So if we actually do the math here, then we're going to get negative 1.415 for this result here and positive 1.415 for this result here. Now remember, because the x and y here were identical, I just haven't done this twice, but it would be the same, right? We would just do it twice for the x and for the y. Then what we're actually left with is an identical x and y coordinate, 1.415. So we know that the answer of the two intersection points are, we have one intersection at this coordinate, and this was the first intersection because the distance along the line is lower than the other one. So this is the closest hit. And then the second one over here has this coordinate here, right? So positive and negative 1.415. Let's go ahead and double check with our graphing calculator, and you can see the answer is the same. Now, of course, square root of 32, I approximated it, therefore we didn't get the exact right answer, but you can see that it is the same, right? Negative 1.414 and positive 1.414. So we have now solved this using all of this algebra and quadratic equation solving math over here. And the beauty is it is exactly the same for a sphere. It's just that you have that z component, as I keep saying. But in terms of how you can work out intersection points and all that stuff, it is exactly the same thing. So yeah, congratulations. All you have to do now is convert this into C++ code and add that third dimension, as I mentioned. All right, that is enough math for one day. So the next step is to try and take like what we've learned here today and actually convert it into code. See if you can use this stuff to draw like an actual circle or a sphere, or at the very least just visualize something. If you can kind of convert this into code, just play around with it, tinker with it, try and draw some stuff on the screen, that'll be tremendously helpful to understanding how it works. And then just go ahead and try and adapt it into 3 dimensions yourself and see if you can make it work. If you do that yourself without looking at like ray tracing in one weekend or any other kind of resources, trust me, like you'll just learn it so much better. Let that be like a little homework challenge exercise for you guys while you wait for the next episode, in which we are going to be taking what we learned here today and drawing an actual sphere. If you enjoyed this video, please don't forget to hit the like button. You can also leave your thoughts in the comment section below. Don't forget to check out Brilliant using my link in the description below, and I will see you guys in the next episode. Goodbye.